Okay. So last time we talked about slip systems.
Slip systems?
Slip systems. That is the closed packed planes and the closed packed direction. Everybody remember that discussion?
Yes.
All right.
This is a really long time ago.
So we talked about the primary slip systems.
Wow.
All right, so for FCC, for instance, we have this slip system. So this is one of the closed packed planes. Just wanted to make sure everybody had the concept, so I'm going back over. And then there are 3 directions in that plane, right? Basically along the diagonals of or the edges of that triangle. So there's 3 slip systems there. Then we move over here, we have that 111 plane, and it's 3, so that's another 6, that's a total of 6. Then we have that one in the back, the green one, and it's 3 for 6, or for 9 now. And then we have the blue in here, and it's 3. So there's the total, all of the primary slip systems for FCC.
Wait,
Yes.
so what exactly does, I don't think we ever really talked about what it means that there's like a line in the plane that it slips through. Like I don't.
So that's the direction. So in other words, if I've got these planes, right, these 2 planes on top of each other, and they've got this arrangement of balls, right, that is the atoms, they can slide into an equivalent position by moving in any of these directions. So if we go back, it's just the blue, right? If it slides by 1 atomic distance in this direction, right, one plane slides relative to the other, it's back to the same kind of condition that it was in before.
So it will slide, it will kind of slide on that plane in the direction of the
Right, because in order for it to slide in another direction, like if it wanted to slide from here out across here to there, right, so this, if you think of this atom, right?
Maybe it would be easier if these 2 different.
Okay. So, in order for this atom to slide, it's got to slide to here. In order for it to slide to there, right, in that direction of the plane, it's going to have to overcome a bigger obstacle because those atoms are further apart. So it's going to have to go, right? It's going to have to slide over a bigger distance in order to go from the bottom corner to the far face center. But going along that bottom face center, the atoms are close together, and so it takes less energy to slide in that direction.
This is like the whole plane sliding, or just
The whole plane sliding, yeah, the whole plane. That's the plane of intersection between the 2 halves sliding, right? Like in a dislocation, it occurs on a plane. Remember when I drew the dislocations up here, the infinite plane into the board? So it's that plane on which it's sliding.
So this is then projected out to the next unit cell.
This is right, projected through the entire thing. Yes?
Why is the if you 0, 1, 0 atom and the 0, 0, 1 atom and the 1, 1, 1 atom, why does that not make its own plane?
The which ones?
No, not that one, Jill. It's these. Okay. This one to that one to that one. So it's like down this way. Why does that not create its own plane? Or
What do you mean its own plane? That's part of this plane. That direction is part of this plane.
oh, like you drew like a plane that cut through this section here. That's a part of this plane.
Which atom? Point.
This one, and that one, like
No,
that.
no, don't point to. Touch the board. That atom,
This
that
one.
atom, and that atom. Those 3 would be a part of, I don't have this one.
Yeah.
That, like, blue would make the blue. Oh, that actually is okay.
Yeah, right, there you
Because
go.
of parallel.
Oh, okay.
It's the
okay.
parallel version of that plane,
That makes sense.
okay?
So then this plane, if you were to imagine the unit cell below it, then the plane that would pass through it would be,
Would be the three on the top face center.
Oh, I'm use this.
that one's wrong.
Thank you, it's very kind of you.
This, 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 this.
And the two face centers on the right and on the front.
Right.
Right. So the cell below it.
That's why, and then that's because this plane is parallel to the one.
Right.
That makes sense.
They have the same plane, just represented from different units. Does that make sense to everybody?
It's not easy.
It's hard to see two dimensions.
Yeah, I know.
We need little models.
But anyway, so the reason, but that's why it has to travel in the close pack direction. So that you've got your thing sliding like this and not like this. Okay. Okay, so now what if we take this cell and actually apply a stress to it? We're going to take that FCC unit cell, actually take the whole crystal, right, but expressed as a stress on the unit cell, and we're pulling it in the 100 direction. So on a macroscopic scale, we have this tensile specimen, we're pulling it upward in vertical direction, right? And we know that it's going to preferentially, it wants to slip on that slip system we've talked about, right? So there's going to be some plane through here on which that slip's going to occur. Right, so this is the plane, this is the one of those 111 planes. That make sense? So that plane has a normal. And there's an angle between the plane normal, what do I use for that? Phi, or whatever that is, theta, I don't know. That, okay. That's the angle between the pulling direction and the normal to the plane. Does everybody understand that picture? Then in that plane, there is a particular 111 direction. Comes off that way. Right? There's a particular direction where we're going to get things to slide. And there's an angle between there, I'm going to call lambda. So we have two angles. We have angle lambda between the pulling direction and the slipping direction. And then we have the angle, whatever that is. I think it's an alternative way of representing phi, but anyway, between the normal of the close packed plane and the pulling direction.
What's lambda again?
Between the pulling direction and the direction it's actually going to slip. The close packed direction.
So that would be kind of like along the oval?
Well, that would be in the plane, right, in the elliptical plane, but in some direction in that plane. But lambda is always defined with respect to the z-axis. So these are direction cosines. These are not, they don't add to 90 degrees. Right, so in other words, if this is the plane, this is the plane, and the direction is off here, corner to corner.
Why would it be that direction?
Because the direction could be, it depends on how the plane is oriented. So the direction could be off there from corner to corner. That's the close back direction. The atoms are lined up in that direction.
Oh, that's the closest back.
Right. So I'm pulling here. The angle between here and this plane is not necessarily the same, not complementary to the angle between here and the direction. They're both with respect to the z-axis. They are direction cosines. Right? Alpha, beta, gamma. Remember direction cosines from statics? Right? These are the alpha and the beta for these two particular directions. Okay? So this and this are indeed perpendicular. Right? The perpendicular to the plane and the direction in the plane are perpendicular, but phi and lambda are not in that same plane. well, I'll show you with the 1-1-1 lattice in a minute, but I just want to make sure you understand, at least have a general idea of what I'm talking about here. So in order to find out what stress we're going to cause on here, we want to know, we got to find first the component of stress. Right, we have this applied sigma. Okay. In the slip direction. And we have to find, let's make that the component of force. And we have to find the area of this, the plane on which it's acting. So what's the component of force acting in the slip direction? It is not F sine of phi.
F cosine lambda.
It is F cosine lambda.
How are those not the same if they're perpendicular?
Because I said they're not perpendicular. Phi and lambda are not complementary. They do not add to 90 degrees. Phi is coming down over here, lambda is coming down over here.
So the normal is perpendicular to,
Right. These
Yes.
two are perpendicular to each other. Phi is over here, lambda is over here. Actually, the way I've drawn it, I draw it like this. Right. Phi and lambda are perpendicular to each other. But my head is not in the plane.
oh, okay.
So this is phi, and this is lambda. Right?
Wait, in the video you could get from that.
Yeah. Watch the video.
We're gonna get a
Okay.
picture of that. Like,
You follow me now?
I got it.
Okay. Okay. Yeah, nobody's, I don't think you're allowed to download the videos from the YouTube. I'm pretty sure it's not. Just what I need is somebody
You take a
taking down
section of
from
it,
making
you
some
can
kind of a gif of me banging my head. Yeah. All right. So what's the component of force in the slip, causing slip? The component of force in the slip direction?
No.
F what?
F cos lambda.
Right, F goes lambda. What is the area of the plane on which that slip is occurring?
Circle.
Let's assume this is A. We're worried about what the exact radius is. The area of the end thing there is A.
don't do this, but Steve, what should happen? It's gonna involve a theta.
It's going to involve theta. Way to go out on a limb with that one there.
I don't know how to say it, I just
Yeah,
can
this-
see what's supposed to happen.
What is the area of that slip region?
It's A times something.
Really, you don't know about projected areas? For those of you who are in thermodynamics, you better learn this because we'll talk about it in thermodynamics as well.
So we'll learn it then.
Yeah, we could have that too.
Probably have to do the closed surface integral.
Probably not.
Line integral.
It's A divided by the cosine of theta.
Oh, close.
Right? Because as theta goes to 90 degrees, that area becomes infinite. And when theta is 0, it's just A. Okay. So what is the stress on that plane then?
Wait, so you've drawn a theta there, but the angle that you.
Oh, phi, whatever.
It's like a zero.
Actually, that means empty set.
Yeah, it means no.
Yeah, you just walk out and let you guys figure this out on your own. Just right, you know. What's the stress then on that plane? How do I calculate stress? What's that?
Force times area.
Nope.
Force
Force
divided.
over.
Right, so the slip force divided by the slip area is going to give me the stress. So that's going to be F cosine lambda divided by A over cosine empty set equals F over A times the cosine of lambda times the cosine of the empty set. Right? What kind of a stress is that? We talked about 3 kinds of stress. What kinds of stress is that? What are the 3 kinds of stress we talked about? Does anybody remember that?
Engineering stress?
No.
Oh.
Tension, compression.
Tension?
Compression.
Compression is actually the same thing as tension, it's just in the opposite direction. It's not a different kind.
Shear.
Torsion is another kind, and shear is the third kind. What are we doing? We're shearing it. Right? We're shearing the thing, right? We're going to pull it, right? That's what we do. That's what we're talking about with our deformation. We're shearing it. We're sliding one plane relative to the other. We're shearing it off, right? So this is a shear stress. What's F over A?
Pressure.
Pressure.
Well, it is pressure.
Not in this case, it's not.
It's stress.
It's stress. What kind of stress is F over A?
Tension.
Shear.
Right, so it's tensile stress.
Instead of a shear stress.
At this point, it's
No,
shear
F over
stress.
A,
Oh.
right? Here, F is in the vertical direction, perpendicular to A, that's a tensile stress. Down here, we have a force in the plane divided by the area of the plane, that's a shear stress. So the shear stress is therefore equal to the applied stress times the cosine of lambda times the cosine of the empty set. We follow that? So what we end up with is a shear stress locally that is determined by the applied tensile stress and the orientation of the crystal. Okay? We call that the, I'm putting critical in parentheses for a reason, the resolved shear stress. So the resolved shear stress is the component of stress resolved to cause shear in the plane that we're interested in. The critical resolved shear stress is the one of those that gives me, because there's multiple slip systems, right? How many FCC slip systems are there? FCC, there are how many?
No, there are 4 planes in total.
12. There are 12 slip systems in the FCC. Not all of them are going to have the same lambda and phi, or empty set, right? They're all going to be different orientation. So the critical resolved shear stress is the resolved shear stress that gives me the biggest answer for a particular slip system. So one of those slip systems, or perhaps many of them, if they're symmetrically aligned, will be the critical resolved shear stress, the one that actually deforms because the tau on that particular slip system is the greatest.
So it would be the easiest way for it to
It'd be the easiest way for it to deform.
So when that breaks, they're going to be like just a slope?
So if this were a single crystal, like this, I pulled a single crystal like this, and it yielded, indeed, they would shear past each other, and I'd end up with 2 pieces with a slice on.
But because it's not probably going to be a perfect.
Generally, we don't do a lot of testing. In real materials, we don't do a lot of testing like this. So this may happen on a microscopic scale, but the next crystal might be oriented differently. So we'll not worry about that right now. Okay, so I'm a single crystal. So this resolved shear stress, and if it's the maximum one, it's the critical resolved shear stress. And then this multiplier here, the 2 cosines, is called the Schmidt factor. Okay,
So, why a cylinder?
what's that?
Why a cylinder?
y of cylinder could be a square, it doesn't matter. Still A, it's still, the thing still applies. I just, typically we pull a cylinder. Okay. Or, yeah, cross, but you could do it with a rectangular cross section, doesn't really matter.
But it doesn't change any of the angles.
No, because it's still just a projection of A down, it's still A over cosine theta. Okay? So, let's consider some different possibilities. Do you understand why this is A over cosine theta? So if I drew this from the side, here's my cross-sectional area, right? Here's my cylinder. Here's the plane on which I'm pulling, right? Everybody see that? Or empty set, sorry, empty set. Here, let me draw this at a slightly different angle so you can see it better. So it doesn't look like it's 45 degrees, okay? So the angle here, this angle, is that's the angle. Right, which is the same as taking the normal and comparing it to the vertical, same angle. So if this is A, this is the hypotenuse, A over cosine theta. Adjacent. Right, something like that. Is that right? No, it was, sorry, it was hypotenuse. This is adjacent. There we go. Okay. Okay, so let's do it for the FCC system. I'm going to switch because well, let's stick with the black. You can probably see the black better than you can. Okay, so let's assume we have FCC. In what direction is this FCC loaded? What direction?
001.
Okay, 001. In the 001 direction. Okay. And I ask you, what is tau, the shear stress, for the most favored slip? In other words, what is the critical result of shear stress? The one that's going to be critical, that's actually going to cause slip to occur. Okay? So, what are the slip systems again? We've got to go through the different slip systems, right? So let's look at that one first. Right? So if that's our slip plane, what is the angle between that plane? Can we find the angle between that plane and the pulling direction? How would we calculate that?
45.
What's that?
45.
It is not 45 degrees. Well, first let's just go through and find out which slip system. This may not be the right one, right? What can you describe qualitatively the distance, the angle between those two? What is the angle of that plane?
Straight.
What's the orientation of that plane? What is the name of that plane? What is that plane? If I told you to define that plane, what would it be?
111.
Right, it'd be a 1-1-1 plane. In fact, this one, if we did, it'd be actually 1 bar 1 bar 1. Right, pick a point that's not in the plane, X, Y, and Z. If I do it by right-hand rule, it's -1 in the X, it would be +1. So it's the 1 bar 1 1. 1 bar 1 1.
Do you need to take the dot product to find the angle between?
So we're going to have to take a dot product, right, exactly, to find the angle. Right, so to find lambda, I'm sorry, empty set. To find cosine the empty set, we have to do the dot product. right? Dot product of the direction dotted with, not square brackets, dummy, right? Divided by the lengths. Right? Dot product is always what you use to find the angle between things. Okay. So in this case, the yellow, I don't have a yellow pen, but we have the one bar, 1, 1, 1 bar, 1, 1. That's the plane, right? What directions in that plane are going to be active here?
Yeah.
What directions are going to be active there in that plane? How many directions are there per plane in FCC? 3.
Well,
Which
it's
ones are going to be active?
The two that have a vertical or a Z component.
Right, the 2 that have a Z component. So really only those 2. That third one along the bottom, I'm pulling perpendicular to that direction. I'm not going to get anything to slide in that way, right? So there are 2, are those angles equal? Right, so what's lambda in that case? What's lambda?
This 145?
What's that?
This 145?
This one's 45,
Okay.
right? Because you can see, here's the direction, and the z-axis, or the c-axis, whichever way you look at it, is the direction I'm pulling. Clearly, you can tell that the angle between those two is 45 degrees. Because the slip direction is in the face plane. It's the face diagonal. So it's 45 degrees from vertical. So I know that cosine lambda is equal to 1 over root 2. Is that true for both directions? It is indeed, right? Depends on which face you look at, but they're both 45 degrees. So those two are equally likely to occur. Okay? Let's look at the next one, right? There's the next plane. What's that plane?
I mean, all of these are going to be the same thing pretty much, right? It's like the 2 vertical ones will be the most likely ones to slip. And they're,
What's that plane?
1 bar 1.
What are you going to choose as your origin for this? I'm just trying to practice to make sure this. What am I going to choose as my origin to determine the plane?
Back corner 1.
We choose that one, right? Bottom right hand corner in the back. So, and remember, A is positive to the right, B is positive into the board, Z is positive up.
1 bar 1 bar 1.
So 1 bar, because I'm going to the left. 1 bar, because I'm coming out of the board, 1. 1 bar, 1 bar, 1. Okay? What are the angles between slip directions? Right? How many slip directions are going to be back active here? Again, 2, because that bottom one isn't active because it's perpendicular. And are the angles between those still 45 degrees? Still 45 degrees. And if I keep going, I've got the green one there. Again, only those 2 are going to be active, and the angles are still going to be all the same. What's that plane?
1 bar 1.
Remember, X is positive right, B is positive back, C is positive up. We're going to use right. So we have 1,
1 bar.
1 bar, 1. Right, see
Okay,
how
but
that's
what if-
different?
So we just have to be, doesn't matter what,
As long as you're consistent.
as long as you're consistent between those 3.
Right.
Like, because in the book, sometimes it would say A is this one, B is that one,
C is that one. Right. Right. And you'll see that. You'll see that. Okay? And then we have the blue one. Again, only 2 are active. And what is that plane?
1 1 1.
That one is 1 1 1. So those are the four that are active. Right? Each of which has two directions that are the same. So we just have to go back here and calculate our cosine phi, and we're all good. So, using the dot product, we end up with, what's the dot product of the directions here? So let's just pick, let's pick this one since we've got it. We've got the 1, 1, 1 plane, and what are the direction, or the, what's the pulling direction?
0, 0, 1.
0, 0, 1.
So it's gonna be 1.
So, and actually the pulling direction should be square. So we have 0 times 1 plus 0 times 1 plus 1 times 1 all over, what's the length of the direction vector? Okay, square, what's this one, the direction, technically it's the direction of the plane. Square root of 1, and the length of the plane vector? Square root of 3. That gives me 1 over the square root of 3.
So it didn't matter which plane you chose or which direction you chose.
They will all be, in this case, they will all be 1 over square root of 3. Now, if I had pulled it in the 1, 1, 1 direction, right? If I was pulling in the 1, 1, 1 direction instead of the, and let's go back to this back corner. Let's use their nomenclature because it makes it easier to see on here too. If I pulled it in the 1, 1, 1 direction, well, let's just leave it here. This is the 1, 1, 1 plane. Where's the 1, 1, 1 direction? Right, it's perpendicular to it. It's going from this corner to that it's the body diagonal. Right? What's phi going to be for that plane?
0. Wait, if you're pulling in that direction.
I'm pulling in the 1, 1, 1 direction.
Phi would be 0.
What's phi? You gotta stay
No.
Phi, okay, null set, whatever. What's the angle between the pulling direction and the normal to the
90
plane?
degrees.
0 degrees. 0.
Because it's the normal to the plane. It's 90 degrees to the plane, but it's 0 degrees.
The angle is 0.
That's right, the angle is 0. Right, so this, the normal to the plane, right,
Is the pulling direction.
is the pulling direction. And what is, so this would be 1. So we're like, wow, that's huge, that's great, right? We got a huge cosine null set. What's lambda? What's cosine lambda going to be? What's lambda? By definition,
Slip direction in the plane.
it's in the plane, so all the lambdas are going to be 90 degrees. Doesn't matter which direction we're talking about. And the cosine of 90 is 0. So if I pull this thing in the 1, 1, 1 direction, this set of slip conditions is absolutely not active. I will not get any slip on that blue plane if I pull it in the 1, 1, 1 direction. However, I will get slip on that direction, in that plane.
Better because he's on a roll.
All right, I don't know why it does that. Sometimes it feels, it always stops halfway through and creates a new video file. It always, I mean, but it's supposed to do it automatically. This, a couple times it stops and doesn't restart the next one, so.
So you get
Anyway,
your lecture
so-
on one video and then pause on
I have to innovate them back together to upload them. That's why if anybody's actually watched the ones where it does that, you get this really weird discontinuity in the middle. Anyway, okay, so you have to try all 12, potentially. Okay, and then look for symmetry, hopefully. Like in this case, if I said I'm pulling in the 1, 1, 1 direction, you say, huh, then I know all my lambdas are going to be, all my cosine lambdas are going to be 0, I'm never going to look at that plane. And then you could look at it and say, well, the green and the yellow are going to actually be the same thing. They're kind of symmetrical about the 1, 1, 1 direction. So I'm only going to do one of those, and then I'll do the red, and we'll see what happens. Okay, so you may have to do as many as 12 different evaluations.
Oh, good.
Oh, good, yeah, lots of fun. So that means then, so in this case, what this means is that lambda is equal to 45 degrees, as we were talking about, and phi, or null set, is equal to 54.7. Okay, those are the two angles. And in this case, getting up on the black, in this case then, the Schmidt factor is equal to 1 over root 2 times 1 over root 3, which is 0.408. So that the resolved shear stress is 0.408, or 41% of the applied stress.
So what does that mean?
That means that if I said I pulled it with, 40 megapascals of stress, I would have just over 16 megapascals of shear stress. And so then I would have to look at it and say, is that going to cause it to yield? Is that going to be elastic? What's the strain going to be? So I now know what my tau is, so I can figure out my G and my gamma.
So if you pulled with that much stress
My G, find my gamma.
exactly in the plane, it would slip, as opposed to some different angle, some G.
So if that was enough to, so basically what it says is if I pull with 40 megapascals, I now have a little over 16 megapascals in the plane. And I've got to figure out is 16 megapascals, right, on my stress strain curve, except now it's tau gamma because I'm talking about a shear curve, and it has this kind of behavior. What is the yield stress in shear? If the yield stress in shear is 12, then I know it's going to shear. If the yield stress in shear is 20, then I know I'm safe. It's elastic. I haven't caused any deformation.
So it's kind of just a percentage of.
This calculates the actual stress. You then have to go back and compare it to the material properties to find out how the material is going to respond to that stress. Yes.
So are you gonna get the most percentage of stress transferred over to it when you're pulling directly along the slip direction?
No, because I'm pulling directly along the slip direction. Then I am by definition pulling perpendicular to the slip plane, and null set will be 90 degrees.
That seems odd.
Right? If I pull this in the 110 direction, along this line, right? I'm pulling in a direction that is, because it's in the plane, by definition, perpendicular to the plane.
Yeah, I get.
And therefore, I will not have any, right? Then the component, right? The area is infinite. There's not going to be any stress.
I get the math. Okay. I get the math, though. I just feel like if you're pulling
If
along,
I've got these two
the easiest
things,
thing
right?
to
If
do-
I've got these two things, right? And I'm just pulling them both together. I'm not. There's no shear. There's no shear, right? So
That makes
I'm just.
sense.
I've got this, and I'm pulling in the vertical direction. There's no shear,
Okay.
right? I'm actually pulling those atoms apart. That's the only way they can move.
But if you somehow grab like this plane and this plane, right, would pull them, that'd be the
Okay,
easiest
but
way.
that's not what you have.
Well, yeah. I just was I didn't
Right.
realize what
It doesn't happen in real life. Come on, dude.
Come on, dude.
Okay, are we good?
Yeah.
All right. Any other questions before I try BCC?
We should get a set of magnetic balls
Actually.
so we can demonstrate this better.
Yeah. Government will come and lock me up. The government will come and lock me up because those balls are illegal. What's that?
Bucky balls?
Bucky balls are illegal.
Oh.
Oh, does it get
I
inside
have-
you?
Yeah, because
Turn
kids
TV
swallow
on.
them. The problem, Nimrod, is that it's a biblical term. Nimrod was a Bible character. The problem is that you swallow two of them
I think it's stuck in
I know.
your
I
temple.
know
at different times, and there are
different.
different places in your intestines, and they hit your
Crazy
intestines.
is like
What
teenage
happens if
ripping
you
out.
bought them before they were illegal?
Good for you. Okay.
Well,
All right.
really,
Reaction over there, Cassie? Okay. All right, so let's go back to the 111 example. Let's go back and do the 111 example, okay? So let's say we're pulling it along the 111. All right, right? So this is this example, and we're pulling it in the 1, 1, 1 direction, right? We know that this one's dead, right? There's no slip there because we're perpendicular to the plane. What about that one? What is the, what is that body diagonal? Let me erase some of the stuff. All right, what is the, I'm sorry, what is the angle between the pulling direction of 1, 1, 1, which is going from front bottom left to back top right? What is the angle of this plane in that coordinate system?
What are you asking?
I'm asking for in the coordinate system we're using,
Yeah.
which is, remind everyone, A, B, C. What is that plane?
The plane?
Right, that plane. Because we're trying to find phi. So we're trying to compare the two.
One negative
Planes.
1, 1.
So, I'm sorry, this is one.
Is it 1 negative?
Right? So that's 1, negative 1, 1. Did everybody see that? And what is the direction if I'm pulling in the 1, 1, 1 axis? What is the direction that I'm going to...
You're pointing what? The 1, 1, 1?
I'm pulling in the 1, 1, 1 direction. Right, so here, cosine of null set is going to equal 1 minus 1 plus 1 divided by the square root of 3 times the square root of 3. Right? That's 1 over 3.
So those, so the square brackets, us telling you what direction you're pulling in, and the
Round brackets of the name of the plane.
the name of the plane or the name of the,
The name of the plane.
okay, then what is the name of the direction in the plane? Of the slip?
Right, so the plane, so what we're comparing here then is the dot product between the 1, 1, 1 direction dotted with the 1, 1 bar 1 direction, because we dot it with the plane, the direction of the plane, which is perpendicular to the plane.
Right, so then, and then lambda will take into account the direction in the plane,
Right.
right?
So what is the direction in the plane?
Which one are you asking about?
Pick one.
Give me one of those guys. Okay. So would that be 1, 0,
0, 1,
1, 0, 0, 1?
0, 1, bar 1.
So we have 0, 1 bar, 1. That is not a plane in that.
0, 1, 1, or
So-
1, 1, 0.
Which one do you want to do? The bottom across, up the left, or up the right?
Dotted
The
one.
left face.
The dotted
Let's
one?
do the dotted one, because that one's clearly distinguished as being the dotted one.
That's
Right?
one bar, 0.
So from here, I go 1 in the x, I go 1 in the y, I go 0 in the z. That is 1, 1, 0. Everybody see that? Yes? The dashed line is 1, 1, 0? Okay. Now let's do the one on the left side.
0, 1, bar 1.
0, 1, 1. Remember, B is positive back into the board in the nomenclature we decided, the system we decided to set with. And what is the third one on the right-hand side?
1,
1,
0, 1 bar.
No, 1 bar. Well, okay. 1, 0, 1 bar, yeah, which is the same thing as 1 bar, 0, 1. They're just opposite directions of each other. Right, one's going up and one's going down. Right? Those are the three directions. So I'm dotting those with 1, 1, 1. Right? If I dot the first one, I get 1 plus 1 plus 0 over square root of 3 times square root of 2, which is 2 over the square root of 6. Does everybody see that? And that's the dot product of 111 with 110. For the second one, I get 0 plus 1 plus 1 divided by the square root of 3 times the square root of 2. So I also get 2 over the square root of 6. For the third one, I get negative 1 plus 0 plus 1 over, it really doesn't matter, because that equals 0. Hopefully you can kind of sense that if I'm pulling in the 111 direction, which means from this front bottom left to back top right, that's actually going to be perpendicular to that face cube, that face diagonal. Okay? So in this particular configuration, if I pull in the 111 direction, that one's dead, the other two are equally alive, and my Schmidt factor is 1/3 of 2 over root 6, which is something really small. I don't know what that is because it's not the most active one. Oh, it is. Yeah, it is. Okay, which is 0.272. Okay? What am I doing? 2 more minutes. What about that one?
Which direction are we pulling?
Oh, first off, we gotta identify the plane first. What's the plane? Using our convention here,
1 bar.
our ABC convention.
1 bar, 1 bar, 1.
1 bar, 1 bar, 1. I'll buy that. So for the red one, we're talking the 1 bar, 1 bar, 1 plane, and what we're pulling in the 111 direction. Okay? So cosine phi, and you always do the plane first, because if the plane is 0, then it saves you doing all 3 of the directions.
We're still pulling in 111.
Still pulling in the 111. So we end up with -1, plus 1 over square root of 3 times square root of 3. That equals 1/3. Actually, -1/3, but just means we'd be pulling in the opposite orientation. So now we gotta get cosine lambda. What are the directions in that plane?
Well, we only need the vertical.
1101.
Bar.
So let's do the dashed one first.
1 bar, 1 bar, 0.
So
Or 1, 1. 1, 1, 0. Or 1 bar, 1 bar, 0.
1
1 bar.
bar. I get 1 bar, 0.
Oh, okay.
Right? So I start in the bottom and start in the back left. I go 1 in the A, -1 in the B, and 0 in the Z. That gives me that
It
diagonal.
bugs me how.
Why are we starting with that?
It bugs me how you can pick.
Because when you're picking directions, you pick a little point on the line. When you're picking a plane, you pick a point off the plane.
It bugs
Didn't
me
you pick
how
the front right corner?
I could pick the front right corner, and then I would have 1 bar, 1, 0, which is exactly the opposite of 1 bar, 0. So it's just the 2 directions, this way or this way, but it's the same direction. Okay, the positive and negative orientation in the same direction. Does that make sense? Yes? We're running out of time, so I want to get the other 2 down there. Okay, what's the next one? With the back face, the one on the back face. Start from the bottom, the back left. We're going to go +1 in the X, 0 in the Y, 1 in the Z. 1, 0, 1. And let's do the front face. 0, 1, 1. Right? Dot product of this with 1 bar, 1 bar, 1, or I'm sorry, with 1, 1, 1 is +1, -1, +1 over square root of 3, square root of 2. So that's equal to 1 over root 6.
One of those should be 0.
Just do, yeah, 1 minus.
Oh, 0, sorry, yeah, you're right, sorry. So that's a 0. Right. So the second one then is 1 plus 0 plus 1 over square root of 3, square root of 2. That gives me 2 over root 6. And the third one is 0 plus 1 plus 1 over the square root of 3 square root of 2, which is equal to 2 over root 6. So it turns out the red one and the yellow one, and in fact the green one, all three have the same Schmidt factor of 0.272. So all three of those are equally active as compared with the one on the bottom.
So is it just random then which ones can slip?
So then, yeah, any of those could slip. And it's probably not random, it's probably got more to do with, you know, where the dislocation, or where the vacancies are and which one's gonna, you know, and actually it'll be a combination of them, because in reality, when a dislocation encounters a vacancy, it can pin the dislocation because there's extra strain associated with the vacancy already. And I don't know if we'll talk about that at some point or not. It seems to me we probably should, but I can't remember. Anyway, so it just depends on the statistical distribution of things and the actual crystal.
Now we can talk about it because we're a day ahead.
What's wrong? I'm not in here.
Turn over.
Can you name the verse that has Nimrod in the Bible? Just